5 programming languages, and today we're going to be talking about building a parse tree. So when we want to build a parse tree, right, there is certain initial conditions that we have to have. One, we need to have a grammar from which we're going to build the parse tree, and two, the string we want to parse that's going to actually end up becoming the parse tree. So once we have that, the procedure is pretty simple. It's at the highest level, it's two basic steps, right? We're going to use the grammar to produce a derivation resulting in the given string, right? I typically do this in my head when I'm doing it, but for really long strings, I would actually use the derivation. Two, we then use that derivation to produce the parse tree. And so there are two different ways we're going to do this. We're going to focus on the first one, which we'll call top-down parsing. And so let's say we have this grammar. This is the grammar that was the inherently ambiguous grammar from the in-class exercise the other day, where we have some string that is going to be composed of at least one set of parentheses and one set of square brackets, or it can be a set of nested parentheses followed by a set of nested square brackets, at least one pair of each. So anyway, we knew this was ambiguous because we could use round or square to generate the parentheses and the square brackets, or we can use outer and the outer inner set to generate the same thing. Anyway, so if we start with this, and we want to derive, so our goal is to create this derivation, and the derivation is basically just saying it's just a walking down the grammar rules, generating the string as we go. So if our goal is to derive the string that we show here, which is a set of parentheses with another set inside of it, followed by a set of square brackets with another set of square brackets inside of it, our goal is to start with the start rule, which is S, right? And we select one of its options. So this is how we generate any string in a language, right? But we need to select a rule such that we will get the string that we are actually trying to derive. So in this case, it's either one. We can pick either of the sets. So I picked round square rather than outer. Once we have that, then we're going to continually replace non-terminals starting on the left, right? We're going to replace all the non-terminals on the left, and then we'll start at the leftmost non-terminal until we have no non-terminals left, right? So it's all terminals in the string. So doing that, right? We start with S, and then we get the first off we get the two non-terminals round and square, and then once we have, then we replace the leftmost one round with one of its possible choices, which in this case was either the set of a start parenthesis round, the non-terminal round, and then the end parenthesis, or the two non-terminals, which is a set of parentheses. And so we chose, in order to gain the one that we want, we chose the opening parenthesis, the non-terminal round, and the closed parenthesis, and that gave us the second line in our derivation. Then for the next line, we replaced the leftmost round with just a set of parentheses, leaving us with the first half of our string, right? So we have the nested parentheses followed by the non-terminal square. So we're going to replace the non-terminal square because it's the leftmost now. So then we look at this and we say, okay, we'll choose one, and the one that will get us to where we need to go will be the start square bracket, the non-terminal square, and then the end square bracket. And then we can, which give us the next to last line, and then we can replace that square with the final part of the string, which is the square brackets itself, right? Just a pair of square brackets replacing square. So that's how we got that string. And this is called, again, top-down parsing, right? And with leftmost replacement. So now we've done that. We solved this. It works out great. Now we can use that derivation that we just created to generate the parse tree. Now, bear in mind, I just used ASCII to show all this, and I'm sure you guys are all excited with my ASCII art. So the first thing we want to do is we start with building the tree. Is we take the root node, so this would be the start node, or the start non-terminal, and that becomes our root, right? And then from that, we branch off with all terminals and non-terminals as the next line, right, or the next level in the tree. And then we follow exactly how we did this, right? So every level in the tree will essentially replicate, but what we're doing is we're just moving this, following the replacement as we went, right? So then we'll replace on round, and so what we did is we replaced round with the terminal open parenthesis, the non-terminal round, and the terminal close parenthesis. That's this part right here. And then we replaced that round with the two terminals open and close parenthesis, as we see here. So then we go and we are going to replace square. So the first thing we did is we replaced it with the terminal open square bracket, then the non-terminal square, and then the terminal close square bracket, as we see here. And then we replace that square with an open square bracket and a closed square bracket. So this builds up the entire parse tree as we expected to see. So it looks good. Now we're done with that. And so that solves this one. So I'll do a second example for this top-down approach, right? So in the top-down approach, we start with we have new grammar. It's the expression grammar. I just replaced the non-terminals with S1, 2, and 3. And so we have plus and multiplication, right, and different precedence levels, and then they're both left associative, and then we have the terminals ABC, and then the expression in parentheses. Okay, so if we were to do this, right, we do a top-down derivation again. So we start out with S1, our start rule, and that can generate S1 plus S2 or S1 plus times S2, or just, it can do S1 plus S2 or just S2, right? But since we know we have a plus, right, we're going to do a leftmost derivation of this. The only rule we can actually apply is S1 plus S2. So then we look at this and we say, well, we need to replace S1 and we're trying to derive A. So the only thing we can do is we can replace S1 with S2, and then we can replace S2 with S3, and then we get A. And then now the leftmost is S2, right? But we need to derive B times C. So we can replace S2 with S2 times S3. And then we need to derive B, right? So S2 becomes S3, S3 becomes B, and now we have B times S3. We can derive from S3 C, and that gives us the string A plus B times C. And then yet again, we can then take this and we can derive a tree from this, a parse tree. And so we start out with S1 as our root. And then we get, from that, we have three children, right? We have the non-terminal S1, the terminal plus, and the non-terminal S2, as we see here. And then we're going to follow the same way we derived it by replacing S1 with S2, and S2 with S3, and then S3 with A. And then we're going to replace the next one, which was, so we have A plus S2, right? So we want to replace S2, and then that gives us three children: S2, the non-terminal S2, the terminal multiplication sign, and then the non-terminal S3, as we see here. And then we're going to replace the leftmost non-terminal with S2 with S3. We're going to replace the leftmost non-terminal S3 with B. And now we're left with the last non-terminal, which is S3, and then we're going to replace that with C. And that gives us the string A plus B times C, as expected. And also we have our parse tree. So it looks great. Alright, so I told you there was another way we can do this, which is called bottom-up parsing. So in bottom-up parsing, we actually start at the top, right? So we're going to use the same grammar from example 2 to derive A plus B times C, but in a bottom-up fashion. In this way, we start with the rightmost terminal and continue to replace with non-terminals until we reach the start rule. So we start out with our string A plus B times C, and then we're going to replace C with a non-terminal S3. And then we look at our rules, and we ask ourselves, should we replace S3 with something else, or can we replace an expression? Well, we see that we have something times S3, right? Is there a rule that gets us there? Well, there is. So let's replace the B non-terminal with S3, and then we can move to replace this whole expression if we shift that S3 to an F2, to an S2, which can be done. And then we can replace S2 times S3 with S2 by itself. Well, then we take a look and we see we have something plus S2, which we know we have a rule for that, which is an S1 rule. It says that we can replace S1 plus S2 with S1. Well, we have to get to S1 plus S2 first. So we can replace A with S3, and S3 with S2, and S2 with S1, and that gives us S1 plus S2, which can be replaced by S1. So that gives us the initial start rule. So we can go from the string to the start rule, or we can go from the start rule to the string. Either way, and then we can build the parse tree the same way as we did before, which will be the same derivation that we saw, except for we're going to flip the derivation, right? Or you can start bottom up and build the tree out, but either way. But you start in the bottom up, right? You effectively want to build the tree in the same, you have to flip the derivation when you do this. But anyway, I will leave that to you guys. This is how you build a parse tree. It's actually quite easy once you see this method, right? This method comes actually from the CSCI book for computational theory. I can't remember the exact page number, but it's in there. It's page 101 to 103 or something like that. You'll find this technique in there and how we derive the parse tree. So have a great day. I'll see you all in class.